All right, so we have to now figure out, learn the second right-hand rule. Before we do the second right-hand rule, let's recall what the first one was. So let's call this one the first right-hand rule. It was like this: if you have a wire and the current flows along this wire in this direction, I, then you take the right hand. You point the thumb of the right hand in the direction in which the current flows, and then you curl your fingers, and the direction in which the fingers curl, like this, around the wire, and that would be the direction of the magnetic field. In fact, magnetic field here would be circular around the wire. And that's the first right-hand rule, and by now we should be comfortable with it. The second right-hand rule is a little different. So the second right-hand rule will correspond to the following. If you have a, well, first of all, let me put it this way. It's going to include a force. It includes a force. The first right-hand rule does not include the force. Second right-hand rule, it includes a force. First, let me sort of indicate what I'm talking about. If you have a magnetic field, here's a magnetic field that points to the right. You place a charge in this field. Here's a charge Q. If this charge Q is moving at some speed V, then there is going to be a force acting on this charge. So if you have charge Q, and this charge Q is moving at speed V, and this charge Q is present in a magnetic field, then you will have a force, magnetic force acting on charge Q. Now, why is that so? I think that's not easy to explain. This is unobservable. We can certainly observe it, but maybe I can give you a hint at why you could justify it. Although it's just going to be a hint, so not really going to be a very in-depth or good explanation. It just gives you an intuition about why this should happen. So if you have a charge, charge that moves generates a magnetic field. And so you would have a charge here that moves. As this charge moves, as it goes from here to here, moving charge produces a magnetic field. And so you would have some kind of a magnetic field set up by this charge as it moves. And in this specific case, the magnetic field would point more or less like this, or weaker behind. But you would have a magnetic field around this around this charge as it moves. It would move in circles around this charge as it moves. Just like if you have a wire and the current flows through this wire, current I, you would have a magnetic field that points the circular way around this wire. You'd have this magnetic field be present around. Likewise, if you have a charge and the charge flows, moves, you'd have a magnetic field around this charge that would be circular due to the movement of the charge. Well, if you then take this charge and you place it in this moving charge, and you place it in a magnetic field that points to the right, so that's another magnetic, then you have some B1, let's call this B1, and you have B2. You have something with magnetic field B1 present in a magnetic field B2. Well, this would be similar to having a magnet within a magnetic field. Let me draw it like this. Here is a magnetic field. Call this B2. And then let's say you place a magnet in here. Say there's a magnet here. And this magnet has a north and a south pole. And so there's a magnetic field that points like this, points around this magnet, and points like this, and like that. So you have a magnetic field due to the magnet here. Now, obviously, the magnetic field due to a magnet has a different shape than the magnetic field due to a moving charge Q. But the point is that you have B1, magnetic field B1, present in magnetic field B2, and therefore you would have some kind of a force. There would be a force on magnet. For the obvious reason that if the magnetic field points to the right, then you would have to have some kind of a north pole here, perhaps some kind of a south pole on this side. So south. Likewise, in this case, you would have to have some kind of a north pole here and some kind of a south pole here, where the magnetic field points from the North Pole to the South Pole. Now, so just like here in this case, if you place a magnet in a magnetic field, you can expect a force to show up acting on the little magnet, and the magnet will move in some way. Likewise, in this case, if the charge moves through the magnetic field, it sets up its own magnetic field. You have B1 and B2, therefore there should be some force. There will be some force on moving charge Q. All right, and so it makes sense to make the statement that if you have a charge that moves through the magnetic field, there's going to be a force on it. Now, suppose that you then take this magnet here, north and south pole magnet. You have a magnetic field present that points from north to south always. And then you place a charge Q in this field. So here's charge Q. But this charge doesn't move. So let's say that the speed of this charge is 0. Well, if this charge doesn't move, then it does not set up any magnetic field because it's not moving. It's as if I had a wire, but there was no current. The current was 0. Well, if the current is 0, then I have no magnetic field present around. So I would have B, due to this wire, to this current, 0 Teslas. And likewise here, if I have Q and the Q just sits there, doesn't move, then there would be no speed and therefore there would be no magnetic field. So in this specific case, if the charge just sits there by itself in the magnetic field, then the force on this charge, the magnetic field force, the force on Q, just be 0. But in this case, since the charge moves through the magnetic field, it sets up its own magnetic field, therefore the force on Q here would not be 0. And there is an equation that relates these. But I'll get to the equation later. Maybe I should just state it. F equals Q cross B. So this is the equation, and this equation comes directly out of experiments. But what I have to show you is how to determine the direction of the magnetic force on charge Q. So I motivated the existence of this force on the charge that moves through the magnetic field. But now what we have to do is determine the right-hand rule, which directly follows from this equation. So now let's go ahead and look at the second right-hand rule. So let's scroll up. Okay, so one more time, the first right-hand rule, that was just about a current that flows, and from here you can use this right-hand rule to determine the direction of the magnetic field. Just points around the wire. Second right-hand rule goes like this. If you have a magnetic field, so let's redraw this thing here. If you have a magnetic field B and you place a charge Q in it, and this charge Q moves at speed V, then there will be a force acting on it. You will have a force acting on this charge. So I'm going to write there will be a force on Q. Right, and so for this reason, the second right-hand rule includes a force F. All right, so now let's play with trying to figure out the direction of this force. So you use the right hand. I'm going to draw a picture here. Here we go. Here's the right hand. There we go. So we have 4 fingers, and then we have this thumb here. Now, this is how it goes. You align your right hand, and this has to be a right hand. If you use the left hand, you will be mistaken. So use your right hand, and then the convention is that along in the direction in which these fingers point, and you keep them straight, the magnetic field points along these fingers. Along the thumb, yeah, let's use red. Well, actually, no, let's keep, okay, so along the thumb, you will have speed v, and actually, let's use black. Okay, so along the thumb points in the direction in which the velocity points. So this is v, velocity. And then you can, if you know the direction of b and you know the direction of v, then you can determine the direction of the force by using the right hand, in that if you set up your hand in this fashion, then the force acting on a charged particle will point out of the palm of your hand in a direction that is perpendicular to the palm. This would be the force on charge Q. All right, so let's draw a few things here. Suppose now that you have a magnetic field that points like this. Here's a magnetic field, it points up like this. You have a charge Q, and the charge Q moves to the right at speed v. You would use your right hand to determine the direction of the force, and the direction of the force would just be in this direction, perpendicular to v. Note that the way I drew it here is that I tried to draw it in 3D, but let me redraw it in 2D instead, because often enough we will just do it in 2D. So magnetic field points up, points like this. Here's B, and then you have Q, and the Q moves to the right, speed V. Here's Q. Then you could indicate the direction of the force by putting a little dot. Should really put this dot on the charge, but I'm going to put it below it, that, and then circle around it, and this is F. The convention is that this dot means the direction out of the page. X, on the other hand, and sometimes X is circled, sometimes it's not, means the direction into the page. Okay. Let's redraw this hand now a little differently. So let's say that you have a hand that looks like this. Here are the fingers. Here's the thumb. Here we go. The magnetic field points always. You align your hand such that the fingers of your hand are pointing in the direction of the magnetic field. You straighten out your thumb, and you make the thumb point in the direction of the speed, direction of the velocity of charge Q, and then you can determine the direction of the force by drawing a vector that comes out of the palm of your hand, the direction that is perpendicular to the palm. There it is. So let's set this up so that we have a magnetic field that points to the left. And then we have a charge, and the charge sits here. This charge is moving in this direction at speed v. There will be a force on it, and the direction of this force, the magnetic force, will be here, where this would be in a direction that is perpendicular to that plane in which the magnetic field is present. So this would be F, force F. Call this V. Now you could again put this thing in 2D so that you would have the picture would look like this. You have the magnetic field, points to the left. So first line, second line, third line, this is the magnetic field. You place the charge Q. In here, this charge moves at speed v, and then you can indicate the direction of the force. It really should be on the charge because the force is on the charge, but that would be too convoluted, so I'm going to put it next to it. That the circle, and F. And this clearly tells me that the force points out of the page towards me. All right, now I'm going to impress you. Okay, so here's a hand, nicely drawn hand. What we need to do is the right hand rule, second right hand rule, is used to find the direction of the magnetic force on charge Q as it moves at speed v through the magnetic field B. So the way to do it is that the direction of the velocity of the particle, you want to align your thumb with the direction of the velocity of the particle. And then you want to align the fingers of your right hand with the direction of the magnetic field B. At that point, you can then see that the magnetic force would be pointing out of the page. This would be force F out of the page. So there's that. And I suppose if I tried to draw it, maybe I could draw it. Although I have a feeling if I draw it, it's going to be just confusing. But because this is almost perpendicular to the... If I were to draw, I guess I could try like this. And indicate that this is 90 degrees. The surface, palm of the hand. All right, that is the right hand rule for determining force on the charge in the magnetic field. So suppose that I have a magnetic field that points like this, and I place a charge Q right here, and this charge is moving in this direction at speed v or velocity v. In which direction will the force point? Well, take the right hand, set it up the way you see it here. It would be easy to see that the magnetic force just points out of the page. Force F. All right, let's try another. Let's try a few more. All right, so here we have a bunch of hands. Now, remember that this is a right hand rule, second right hand rule. That it is not left hand rule. In other words, you can't use your left hand. So let's see what we have. This looks to me like the right hand, so we can use this. This looks to me like a left hand, so I can't use this. This looks to me like a left hand, so I can't use this. This looks to me like a left hand, so I can't use this. And this, I think this is also a left hand. Yeah, this is a left hand, so we can't use that either. The only hand we can use is this. Now in this specific case, the magnetic field is always to point along these fingers. So this is B. Direction of the speed or velocity. It is a scalar. The direction of the velocity would be along the thumb. So you would have that V pointing there along the thumb. That's V. Pretend with me that this thumb is actually pointing up, not into the page, because the way this is drawn, it's just that this thumb is pointing into the page, but you don't want that. You want this thumb to be sticking out like this. All right, so here's the thumb, and then V is pointing in the direction in which the thumb is sticking out. Now, if this is the case, then the magnetic field, rather magnetic force, always comes out of the palm of your hand, and it is perpendicular to the palm of your hand. So in this case, it would just be into the page. Now let's draw it in black. So this would be into the page. This would be force F. Let's draw a case where this would be actually happening. So let's say the magnetic field points to the right, like this. This is magnetic field B. And then you take a charge and you place the charge here. So here's charge Q. This charge Q is moving at speed V upwards. In that case, take your right hand. I'm actually going to draw this. And align it in such a way that the thumb points in the direction of velocity V. And the fingers straighten them out, point in the direction of the magnetic field. And And then and this is the right hand. And the force comes out of the palm of your hand. So the force would be pointing, start here, and then it points out of the palm of your hand, extends like that. Here's your force F. So it would be into the page. You would put this as the force F, it's into the page. Into page. Okay, so at this point, what we should do is, I'm going to draw a bunch of different cases, and then we'll try to determine the direction of the magnetic force. All right, so we have the right hand. Let's remember what it was. B points in the direction in which the thumb is stretched out. That's the velocity. Magnetic field is aligned with, or rather the fingers of your hand are aligned with the magnetic field B. And then force is coming out of the palm of your hand in a direction that is perpendicular to the surface of the palm. So let's try it. So let's say here goes out like this. All right, and this would be perpendicular to the palm of your hand. Or I could just redraw this thing down here. This is B, this is B, and then force F points like that. It's like the coordinate system where you have X, Y, and Z. So I'm going to draw this here next to it. This is Y, this is X, and then this is Z axis. Same thing. All right, so let's try it. So let's say we have something like this. Here's the magnetic field. Magnetic field points to the right. And let's say we have, let's do it like this. The magnetic field points to the right all the way here. Let's take couple charges. So let's say that we have a charge here that moves in this direction, B. Let's say we take another charge, and this charge here moves in this direction, velocity V. Let's add a few more lines of the magnetic field. Let's say that this charge here moves in this direction. Say that this charge here moves in this direction. Now let's take a magnetic field. Let's have it point like this. Put a charge. Say that this charge moves in this direction at speed v. That the blue one is the magnetic field. And let's say that this charge here moves at speed v, but in this direction. Let's leave that's q and this is v. And let's say that this charge q moves in this direction at speed. And then let's do the following. Suppose that you have a magnetic field that points into the page. So here's the magnetic field that points into the page. Let's set it up big enough so that we can put a few charges into this field. So this magnetic field is pointing into the page. Then you take the charge Q and you put it here. In a second, let me figure this out because I want to get somewhere with this. So it points this way, therefore the force is like that. What I'm gonna do with the, okay, yeah. So let's put a positive charge here and let's say that it moves at speed v in this direction. Let's put a positive charge here. Let's say it moves at a positive in the direction. And maybe we'll do one more charge here. Positive charge going in this direction at speed v. Okay, you can pause the video and then you can try to figure out the direction for all of these, the direction of the force for all of these charges. And in the meantime, I'm going to go ahead and I'll start doing it. So I'm going to align my hand in the direction of the magnetic field. I'm going to do this first. And in this specific case, my fingers will always have to point in this direction. For the first case that I have here, I have to draw my right hand like this. Fingers point like this. One. The thumb goes this way. This is the right hand. That implies that the force comes out of the page. The first one, the force just comes out of the page. I'm going to indicate it like this. Here's the force F out of the page. Let me put this on the side. This is out of page. This is into page. Okay, in this case, I would have to draw my right hand. This thumb points this way. This is first finger, second, third, fourth finger. Right? And so then the force here in this case would be pointing. Remember, this is the right hand. This is the right hand. The force here comes out of the palm of my hand, and so it'd be into the page. Right, next one. For this one, what I would have to do is I would have to draw my right hand like this. The thumb is slightly at an angle. That's fine. 1, 3, 4. And remember that this is the right hand. So then the force comes out of the palm of my hand, and so this would be still into the page. Force is into. In this case, well, you could either break your thumb, or you could flip your hand so that what you have is. Let's see if I could do it. Actually, I can't do. Actually, I could. All right. So what you would do is these are your fingers. They always point. They always align these fingers in the direction of the magnetic field. So I have 4. Then your thumb would point like this. That's not bad, actually. I think that works. And so, and just remember that this is the right hand, not a left hand, it's the right hand. And so the magnetic force, the force on this charge would point still into the page. This is, wait, no, that's wrong, actually. This one is not into the page. Let's get rid of this. This would be out of the page. This here would be out of the page. Here's force F. This is out of the page. All right, that's in. That's in. That's out of. This is out of the page. Okay. All right. So these are the directions of the forces. Let's do this one now. Magnetic field. So going with the first one, you would have your fingers pointing in the direction of the magnetic field. So these are the fingers. 1, 2, 3, 4. Here's the direction of the velocity. This has to be a right hand. Has to be right hand, and that implies that the magnetic force on this charge point comes out of the page. This comes out of the page, so I'm going to put here that F. Good. Next one over. Magnetic. The fingers have to point in the direction in which the magnetic field points. I would have 1, 2, 3, 4, but my thumb is to point the direction of the velocity, and this is the right hand. So the only way this could work is if the force was pointing into the page. So if the force is into the page in this case. So the fingers point in the direction of the magnetic field. 1, 2, 3, 4, and then the thumb does this. This is the right hand. The only way this could work is if force was pointing into the page. All right, let's do these 3. And then I think we're all set with the right hand, though I have to make a simple comment about the negative charges. But so for this case here, what I have is, oh, that's going to be tough to draw. The magnetic field here points into the page. Looking at this charge, the magnetic field points into the page, and I think I can draw that. Yeah, because I think if I draw it, that would just be confusing. So in this case, the I guess I could try it. If it comes out bad, just ignore it. But so first finger, second finger, third finger, fourth finger, and here's the thumb. This is the palm of your hand, and this is the velocity direction, and the magnetic field points into the page. Magnetic field points there into the page. The force acting on this charge would come out of the palm of your hand. go up. Of course. This makes sense, that's good. This is actually not too bad. I have to say this is not bad at all. The point is that the force would point like this. Now, looking at this chart here, so let's try drawing this one. Yeah, let's try this one. I think this is going to be a little easier maybe. So what I would have to do here is well, I would, here's a finger, second finger, fourth finger, and then my thumb points to the right. This is my hand. The force would go down the page. So if I were to draw a force now, I would have to do something like, if I start in the middle of my palm, that, let's suppose that your hand ends. This is the direction of the force. So I would have the force that points down. This one on the top. So if I have this one here, then my fingers would have to point, well, it's just, hopefully you can see this one, but this would be, the force would point to the right. So the force points to the right. Okay, now so we have the right hand here. So what happens though, a couple things. First one is, well, all right, this is perhaps good and well, but what happens if instead of a positive charge, you have negative charge? So let's say that you have, well, let's maybe keep that. Let's keep the picture here. Suppose that you have an magnetic field, and the magnetic field points to the right. Let's take up this space here in the corner. Points to the right. And let's say that you place a positive charge here, and you make this charge move at speed v downwards. In which direction does the force point? Well, it points into the page, or rather out of the page. It's F. Let's confirm that actually is true. Yeah, so this would point, the force here would point out of the page. Now, if, on the other hand, you have a negative charge, and the negative charge is moving down at velocity v, then the force would, probably would suspect, would have to flip. The direction of the force would flip. The force, the magnitude of the force would actually still be the same, but direction flip. So if I redraw this whole page, and instead of all of the positives, I put negatives all over the place. So let's say that I just do it so that this is now negative, and this is 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 negative, and so also this, and this is negative. If that were the case, then I would have to redraw all of the forces and state them in that they point in opposite directions. So this one would point into the page. This one would point out of the page. This one would point out of the page, and this one would point into the page. I think you get the picture. If that was a negative instead of a positive, then this would point into the page. And if this was negative instead of positive, this would now point out of the page, and so on. I think you get the idea, but let's maybe do that. So this wouldn't be true. Instead, the force would point in the opposite direction. This wouldn't be true. Instead, the force would point in the opposite direction. And this wouldn't be true. Instead, the force would point in the opposite direction. Okay, so now you know how to use the right-hand rule for positive Q and for negative Q.